In this video, I want to have a look at something called T formulas or T results. So one problem that we sometimes come across is when we're solving problems that involve sine, cos, and tan, is that sine, cos, and tan aren't like terms, so they don't always interact very nicely. So we know from the mathematics course that we can manipulate our trig, our sine, cos, and tans using our trig identities to rewrite them in other forms. But some manipulations are going to be nicer and easier to work with to make them into like terms so that they can interact. So what we're going to have a look at today is a specific manipulation, and we're going to write sine theta, cos theta, and tan theta. We're going to write them all in terms of tan theta on 2. Now, the reason we write them in terms of tan theta on 2 is because it turns out to be the nicest manipulation. So we could write all three of them in terms of sine theta, but it gets a little bit messy. Same with cos theta and tan theta. So this one actually turns out to be the nicest. So let's have a look at how we're going to do that. So the first thing we're going to do to derive these formulas is we're going to write let t equal tan of theta on 2. So that's our half angle there. And we're just using t just to make this a little bit shorter and neater. So now to derive our formulas, we're going to use our double angle results. So we'll start with tan. We know that tan of 2 theta is equal to 2 tan theta over 1 minus tan squared theta. So in this formula, this angle here is double these ones, or we can say that these angles are half of this one. So we could rewrite this formula as tan of theta is equal to 2 tan theta over 2 over 1 minus tan squared theta over 2. But we know that tan theta over 2 is t, so then we can shorten that to 2t over 1 minus t squared. And this here is our first t formula. Now to get our t formulas for sine and cos, we're going to have a look at a right-angled triangle. So if we call this angle down here theta over 2, so that's our angle here, we know that tan theta over 2 is t. So tan is opposite over adjacent, so that would have to be t over 1. So from there we can use Pythagoras' theorem to figure out the length of the hypotenuse, which would be the square root of 1 plus t squared. So if we have a look at sine first then, using our double angle result, we know that sine 2 theta is equal to 2 sine theta cos theta. Now again, these angles here are half of this angle, so we could rewrite this as sine theta equals 2 sine of theta over 2 cos theta over 2. And then we can use our triangle to find these. So we're going to have 2 times sine theta over 2, which is opposite over hypotenuse, so t over the square root of 1 plus t squared, times cos theta over 2, which is adjacent over hypotenuse, so 1 over the square root of 1 plus t squared. Now if we multiply numerators, we'll end up with 2t, and if we multiply denominators, we'll end up with 1 plus t squared. So this is our second t formula. And our last t formula is going to be cos, or come from the double angle result, that cos of 2 theta is equal to cos squared theta minus sine squared theta. Now again, we'll rewrite that. So we're going to have cos theta is equal to cos squared theta on 2 minus sine squared theta on 2. Now we know that cos theta on 2 is 1 over the square root of 1 plus t squared, but because it was cos squared, that whole thing's going to be squared. Then we're going to have minus t over the square root of 1 plus t squared squared. So if we expand out those squares, we're just going to have 1 over 1 plus t squared minus t squared over 1 plus t squared. And because they have a common denominator, we can just put those together. So we're going to end up with 1 minus t squared over 1 plus t squared. And that is our final t result. Now it is important to know that this way that we've derived these results isn't actually a formal proof, because we've used a right angled triangle here to find the length of the hypotenuse. But that's assuming that there's a restriction on this angle of theta on 2, that it has to be less than 90 degrees. It has to be an acute angle. So these results actually work no matter what that angle is, but we've restricted it here. So there is another proof that you can use that proves it and doesn't have that restriction, but we've gone with this one just because it's a little bit easier to understand. Right, now these formulas are on your formula sheet. So we're going to go through now and use these to solve a couple of problems. So our first one asks us to find the exact value of 1 minus tan squared 15 degrees over 1 plus tan squared 15. So having a look at this, we can see that it's in this form here. So cos theta is equal to 1 minus t squared over 1 plus t squared if t is equal to tan theta on 2. So in ours, it's only going to work when this is the half angle. So that means that our theta on 2 is our 15 degrees, which means our theta would have to be 30 degrees. So this here is going to be equal to cos of 30 degrees, which we know from our exact values is equal to root 3 over 2. So the exact value of this whole thing is root 3 over 2. Our second problem asks us to prove that cot of theta on 2 minus 2 cot theta is equal to tan theta on 2. So we're going to start with the left-hand side of this equation. So we've got our cot theta on 2 minus 2 cot theta. Now that's going to be equal to 1 over tan theta on 2 minus 2 over tan theta. Now we know that if we let t equal tan theta on 2, then this is just going to be 1 on t. And we're going to have tan theta is equal to this 2 over 1 minus t squared. 2t, sorry, over 1 minus t squared. So I'll leave our 1 over t. Now if we're dividing by a fraction, we can multiply by the reciprocal. And from there, our 2's could cancel out, which would just simplify this down to 1 over t minus 1 minus t squared over t. Now they have a common denominator, so we can put those together. We just need to be really careful about this minus minus. So we'd end up with minus 1, but we'd end up with a plus t squared there. And that 1 minus 1 is just going to give us a t squared over t. I'm going to have to move up here. And that would simplify down just to t. And we know that t is equal to tan of theta on 2, which is equal to our right-hand side. So we've proved that identity that they've asked for. Our third example asks us to prove that tan 2x cot x equals 1 plus sec 2x. So we're going to start with that left-hand side again. So the left-hand side is equal to tan 2x cot x. Now this can be proved using our trig identities that we used in mathematics. But when we're using those identities, we often had trouble being able to see what the next step should be and what manipulations you should make to get to where you want to be. So in this example, we're going to go through and solve this using t results, and you can see how it's sometimes a little bit clearer as to what you should be doing. So this time, because we've got tan 2x cot x and sec 2x, we're going to not let t equal tan of x on 2. We're going to let t equal tan x. So our x is our half angle. So what that means is that this tan of 2x is actually our angle, so it's like this guy. So our x was our half angle here, and this is our double angle now. So our tan 2x is going to end up being our 2t over 1 minus t squared. Our cot x, that's equal to 1 over tan x, and we just said that tan x is t, so that gives us our 1 over t. And our sec 2x would be 1 over cos 2x, which is just going to be the reciprocal of this one here. So that's going to be 1 plus t squared over 1 minus t squared. Now to prove this, I'm going to start with my left-hand side. I'm going to simplify it down. And then I'm going to actually jump to my right-hand side and simplify that down, but show that they simplify to the same thing. So substituting these in, I'm going to have 2t over 1 minus t squared times my cot x, which was 1 over t. So my t's would cancel, and I'll just end up with 2 over 1 minus t squared. So that's what my left-hand side can be manipulated into. My right-hand side was 1 plus that sec 2x, which is this here. So 1 plus t squared over 1 minus t squared. Now, if I make them have a common denominator of 1 minus t squared, I would have to multiply this one by 1 minus t squared. So I'd have 1 minus t squared plus 1 plus t squared. Then my t squareds cancel out, and I'll just end up with 2 over 1 minus t squared. So then I can write, therefore, my left-hand side is equal to my right-hand side. So it does take a little bit of work to set this up in the first place, but once you've set those up, it's fairly straightforward proof. So there's no big leaps of knowing where you need to go and what manipulations you need to be able to see. So this can be a really nice manipulation to solve problems involving sine, cos, and tan.